Hey everybody, so today we're going to be looking at redox half reactions. We're looking at redox reactions in their reduction and their oxidation steps. We call those half steps. So starting off with, if we're looking at a reaction that we've looked at before, the reaction of sodium and chlorine to produce sodium chloride. To keep it balanced, we know that if we're looking at this equation, sodium exists just as a free kind of metal where the atoms aren't necessarily bonded to anything, so we just write that as Na. Chlorine, though, exists as a diatomic gas in the atmosphere, so Cl2. The result is NaCl. We know that by looking at, we went through Lewis-Stat structures. We know sodium has one outer shell electron, gives that up to become sodium with a charge of +1. And then we also know that chlorine, one chlorine atom, has 7 outer shell electrons. And it's going to take another electron to become chlorine with a charge of -1. And that works out pretty well for us. But there's another way that we're going to look at redox reactions here. So let me go ahead and delete this stuff. All right. So looking at this, looking at that half reaction there, we have a couple of things going on. We know that sodium chloride, this product here, is a mixture of a metal and a non-metal. We know that's an ionic bond. So the first thing we have to do is form our ions. That's what the oxidation reduction steps really help us figure out, is which ones form the positive ion, which ones form the negative ion. Because looking at this right here, if you knew nothing about sodium and chlorine, you wouldn't know which one's positive, which one's negative. So we're going to go through that quick. So before, we kind of went through, looked at sodium's outer shell electron, says 1, gives them up to form a +1 charge. However, so let's go through this. So we have sodium is essentially becoming a +1 ion, and it's getting rid of an electron. The shorthand for that is just little e with that superscripted negative sign there. However, according to our reaction up here, we have 2 sodiums. So that means down here, we need to double everything. Now, part of this is also going to tell us whether this is our oxidation or reduction step. Remember, we have a shorthand for that. Leo goes GER. Lose electrons oxidation, gain electrons reduction. Okay. So in this case, we're looking at it, and it looks like our sodium here, as messily as that too, as I fit that in there. This right here, this is our oxidation step. We know that because the sodium is losing electrons. All right, so let's look at the chlorine now. If we look at chlorine, once again, 7 outer shell electrons, that's going to take 1 to get up to 8. So in this case, the chlorine is going to take 1 electron to form that negative chlorine ion. Now in this case, chlorine is taking an electron to form that -1 charge. Lose electrons oxidation, we're not doing that one, so we have to go to the second part. Gain electrons reduction. This part here, this is our reduction step. Now some of you may have already noticed this only accounts for 1 chlorine. Up here, we have 2. So we need to essentially double all of this. Let me try to get rid of that. All right, so go through here. We need to double that, double that, double that. All right. So then we also have kind of one of the next things we could do is we could also write the Na plus combine this step with kind of all of this. So if we have, let's start over here. So we have 2Na. Essentially, I'm going to write this stuff. I'm going to write all of our products together. Plus 2Cl plus 2E negative. Right? Because according to both of these reactions, these are our total reactants. And then I'm going to write all of our products together. 2Na plus 2E negative plus 2Cl negative. All right. Looking at this, we can, anything that's the same on both sides we can get rid of. So these electrons here, we're going to cancel out. So this is kind of the combination of our oxidation and reduction steps. However, and we can leave it here because essentially this is occurring in water. So it's all dissolved in water where we know our ions kind of stay separated. So this would be, this part right here would be our net ionic equation or reaction. Net ionic reaction. Really it's just a combination of the oxidation and reduction steps where we keep the reactants on one side, the products on the other, and kind of get rid of anything that's the same. Like we know by looking at the oxidation step here that the sodium is giving up 2 electrons. And then looking at the reduction step, the chlorine here is taking those 2 electrons to become negatively charged. All right, should we look at another example? All right, let's go edit and clear. All right. So the next example we're going to look at is we're going to keep looking at, actually we're going to move to aluminum and oxygen. 4Al plus 3O2 becomes 2Al2O3. We can do some basic math to make sure that this is in fact balanced. We have 4 aluminums here. 2 times 2, 4 aluminums there. 3 times 2, 6 oxygens. 2 times 3, 6 oxygens. So we're good there. Next thing we need to do is we need to figure out what our oxidation and reduction steps are. Most of the time, I would suggest starting with your reduction steps because your negative ions are much easier to work with. So let's go ahead and start with, so let's go reduction. So we're looking at the one that is going to gain electrons. Typically this will be the one that is becoming a negative ion. And we know our non-metals become negative ions, so we're going to be looking at the O2. So let's go ahead and just write a note here. I'm going to leave space so I can bring some numbers down here. Oxygen, if you look at your periodic tables, 6 outer shell electrons, takes 2 electrons, and that gives it its 8 electrons. Big thing though, you can have a charge negative. I should give myself some space there. Alright, so now I'm going to look back up at the equation there, and I'm going to see I have 6 total oxygens on both sides. So I need to put that as 6, make that as 6, but now with that 2, I'm going to have to take 2 times 6, because if every oxygen is giving up 2 electrons, and I have 6 oxygens, 6 times 2, I have 12 total electrons that those oxygens all need to take. But the big thing here, my reduction step's done, so let's look at the oxidation. All right, so now that we know we're looking at the aluminum there. With the aluminum, we already took care of reduction. We took care of the one that's gaining electrons. So in this case, we're looking at the thing that's giving up electrons. So we only have the one reactant for the oxidation half step. Aluminum, if we look at the, well, let's look at it this way. I have 4 aluminums here. I know that with it balanced, the number of electrons here needs to equal the number of electrons here, so that's going to be 12. I just need to figure out what charge does that aluminum have afterwards. So I have 4 aluminums. Together they give up 12 electrons. figure out how many electrons each aluminum gave up, I just take 12 divided by 4. So that tells me my 4 aluminum atoms are now positive 3 ions. So essentially 12 divided by 4 gets you 3, and that's the charge on each of those aluminums. Now we can write the net ionic reaction. RXN, by the way, short for reactant. All right. One thing I can see right away, 12 electrons here on the reactant side, 12 electrons here on the product side. Those are going to cancel each other out. So really I have 4Al plus 6O becoming, keep in mind, our electrons canceled, 4 of these positive 3 aluminum ions plus the 6 negative oxygen ions. All right. And here we can do some math to figure out that these are going to combine, when you crisscross them. For each kind of formula unit, we're going to have 2 aluminums and 3 oxygens. And altogether, we're going to end up with 4 aluminums and 6 oxygens, which, looking back here, we can kind of see. Now you may be asking, why do we go through all of this trouble if we can balance it the normal way? It's important to know how many electrons are being given away and how many are being taken. Because when we move on to electrochemistry, we're looking at the production of electricity. That's all about the flow of electrons. So we need to know, where are these electrons coming from and where are they going? Looking at the redox reactions we looked at today, they're pretty basic. We're looking at metals and nonmetals, things forming positive and negative ions. The issue when we get to electrochem is we're not worried at all about the nonmetals. We're going to have metals that are gaining and losing electrons. So this kind of helps ease us into this, being able to recognize reduction and oxidation reactions here is going to help us when we get to electrochem. So this stuff is important. It relates to even how like a lithium-ion battery works, or how like a AA battery works. This kind of explains it. This is our first step to kind of understanding. So with that, I have some practice problems for you guys. Good luck.